Good afternoon and welcome to the Sensors and Sources session in the Northern 2014 conference. So let's start. In the program we will have 3 speakers in this session. First of them is Walter Schmidt from Finland.
Yeah, that's me.
And he will tell us some results, or perhaps some results to be seen from the Rosetta mission. And our second speaker will be Anders Roch-Gregersen from Vestas, and he will tell us about some results of wind measurements, I believe. And concerning the third speaker, I have an apology to you. So our third speaker would have been Richard Jero, and his topic would have been ash cloud measurements using X-ray radars, but unfortunately he couldn't come. So his special interest is volcanoes, and as you know, there's one erupting at the moment in Iceland, and he's the one measuring that volcano. So I think we consider this a very good excuse. But without any more delays, Walter, please start.
Thank you for giving me the opportunity to speak here to you. And as it is a rather perhaps strange topic for quite some of you, please feel free to interrupt me anytime with questions already during the talk. As you heard, we have anyhow one slot free, so we'll have a little bit more time to this. Okay, I'll start with this mission you might have heard about in the news, and that is what the European Space Agency called Rosetta, by which we try to find out much more about the origins of our solar system. That's where this Rosetta Stone idea came from. And it's going to this comet with the not that easily pronounceable name, Churyumov-Gerasimenko, or in short, 67P, which is the official name. It's much shorter, of course. So what I'm talking about is, first of all, what this mission is all about, and what the problems are, which we already did encounter and which we are still expecting to see. Then the major part of this first section will cover the capabilities of the instruments, including some of the results as far as they, for once, already exist. And B, I'm allowed to mention them, for ESA has a very special publication policy there in order to give the principal investigators of the instruments the possibilities to publish their news first themselves. But that leads then directly to the properties of the comet as far as we saw it already during the last 3 weeks of measurements, for we are already very close. And finally, a little bit back to what this conference is all about, and that is how actually to make use of this vast amount of data coming from very many different sources, and how to be able to combine them in a way that scientists, not necessarily specialized in this given instrument, but only in the wider field, can make use of it. Okay, let's start with the Rosetta mission. So first of all, the spacecraft, which was launched 2004, is about 3 times 2 meters, so 2 meters height, and then about 2.8 times 2.5 meters. So nearly a cube, a heavy one, nearly 3 tons. And then it has very large solar arrays, 40 meters in each direction, in order to get as much power out, even being far away from the sun. And I'll come to that in a few minutes, and we'll see that even that wasn't quite enough. Quite a lot of that mass is actually propellant in order to get it there where it is now, but even more important, to help it drive around a comet. For as you can imagine, the comet is not a planet where you can orbit around and the gravity takes care of it, but it's a mathematical point in space. You actively have to drive around, make corners, and keep up with the comet in the middle of that square or whatever kind of geometrical figure you want to drive along. Okay, and part of this whole spacecraft is 165 kilos of payload or scientific instruments for a wide variety of measurements. And additionally, it has this little lander, and also 100 kilos, which for the very first time in human history tried to actually settle on a comet's surface. I tried to avoid the name landing, for landing kind of implies gravity, which isn't. So, and the maneuver precision they have with this system, which is rather incredible. So it's 1 millimeters per second relative velocity. They can adjust things. And even that is rather a challenge, for there might be, and there is, gas coming out of the comet, which might move all the control notwithstanding the spacecraft a little bit into other directions than they wanted to. And it's not that much a joystick mission, for the commands in one direction even now takes still more than half an hour. So before they see a reaction, decide what to do about it, and actually having that corrective command arriving at the comet, it's already 1.5 hours gone. Okay, so what did it do? We started with a year late due to the fact that the launcher, Ariane 5, had some major failure, and the original launch for 2003 was cancelled. So the comet we wanted to go to in a much shorter time frame was gone. So they had to look for another comet, which is this one, a bit larger, a bit heavier, a bit more difficult to get at. But nevertheless, eventually the launch worked perfectly in March the 2nd, 2004. And in order to get out to the Jupiter orbit, which is rather far away without using too much fuel, one is using gravity assist, as you know. So 3 times it came rather close by Earth and was slinged out even further. And once in between, it passed Mars for the same purpose, which happened then to be rather at the right location. And eventually it flew all the way out to the Jupiter orbit, bringing it so far away from the sun that the solar panels really didn't provide much more power than just keeping the computer and the real-time clock running, so they had to cut off the telemetry, for the transmitters take too much power. And so the whole thing was spun up and stabilized by rotation, and then it was lost intentionally for 31 months. You can imagine what our feeling was in January the 20th, when this thing was scheduled to wake up again and then say, hello, here I am, which means I had to wake up, stop spinning, looking at the sky to find out where it is, analyze the stars, calculate where Earth might be, turn the whole spacecraft around to point the antenna to that direction, and then send a signal. And when the moment came, nothing happened. 45 minutes later, fortunately, this signal came. What had happened, as usual, you know computers, the moment it started up, it crashed. So it had to reboot and go through the whole reboot cycle, which took these 45 minutes. Okay, so everything's fine, and it's matched then eventually during summer the trajectory of the comet, and now you can't really see that, but anyhow, here we are. You might be able to see it so at yeah, basically tomorrow. So you have the figures there. It's about 494 million kilometers away from the sun. So and the distance here to the Earth is a bit shorter, for we are a little bit to the side. And just to give you an impression of the solar system, the inner part at least, and up in the left corner you see Jupiter. You have the Earth roughly above the green arrow, and then the sun in the middle, and you have the different planets they're round. I'll come to this picture once again a little bit later. So, and what you see there are these funny lines which tell how actually the system eventually came to where it is now. So, very complex. On the right-hand side, so on this next one, you see actually a close-up of the camera showing that it worked nicely. Looking underneath the solar panels towards the surface of Mars when it flew by. And then from there it came over to Earth a little bit later. And there was a little side joke when it approached Earth. Obviously the Martians didn't like that close approach, so they sent a fighter following it. And only when it came too close to Earth, it just veered off. So it looked on the telescope. Directly, once it came away after Mars, some other object came directly after it. It was nearly the same velocity, slightly catching up, and then once it came close to Earth, it moved the other way. It was just an optical illusion, of course, but it's a nice side story. So the Martians were not that happy about this close-up. And that's the camera from the landing unit. I'm coming to that later. So it didn't do nothing for the last 10 years, but actually the trajectory brought it close to 2 asteroids, actually very close compared to astronomical distances, so 800 kilometers only. And that's close enough so that the gravity of this asteroid is slightly influencing the trajectory of the satellite, and thereby also per Doppler effects the properties of the transmitted signal. And it has a very high, the ultra-high stabilized clock on board, synchronized with Earth, so that you really can follow that. And as a basis of that, they were able to then measure actually lots of details, which are then calculated in different ways. And of course, there are also other analyses and surface spectroscopy. And so you see it's iron poor silicates is there. It's about 20 million years old. And it's rather a big thing, 76 cubic kilometers, and so on and so on. So, and doesn't have any measurable magnetic field. Okay, so that was was Steins, and then it followed its track and arrived at another one, even a little bit close eventually, but this one was already a rather nice picture here. So you see rather smooth surfaces, and had actually never happened to get that close to this asteroid, and they measure them with that precision. And then eventually it arrived this summer at the comet, and this is a rather unique picture. Again, the same field of view I have shown earlier when it flew by Mars. So you see the solar panels now on a slightly different angle to point it directly to the sun. But above that, you see already the comet. It's very funny shape. So that was still 285 kilometers away. Now it's at about 60. So we know much more about it. Okay, I'll come back to the properties of this comet a little later. Now let's shortly go through the instruments. What do we want to measure and what can we measure? One of them is the so-called cometary secondary ion mass analyzer, short COSIMA, which is a folded mass spectrometer with a very special inlet part. Inlet part means there's a little table which can catch, and did already catch, cometary dust grains, and then move them around underneath a microscope to find the proper location of a dust grain, and then use an ion cannon, with Indian ions actually, to ablate the surface material of this grain, one layer after another, which are then accelerated into the mass spectrometer, and thereby you get analysis of the tomography of a cometary dust grain, never done before. We had something similar in an easier way on Stardust, a predecessor of the same team. Actually, it's my colleagues who are analyzing the data, and we built the software and everything to that. So with that, we'll get for the first time also exact shapes of cometary dust grains. And what's so special about that? It's very easy. So far, we know comets from mainly telescope observations. In order to interpret them, one has to make some assumption about the reflective material. And the assumption normally is, for that's mathematically the easiest, that it's spheres. But the only reason really to use spheres, it's easy. And they're certainly not spheres. And if you use the real shape, real reflectivity, refraction index, and so on, you can find out then how to actually, even old data have to be corrected to get you closer to what the object really was like. So that's what we will be doing with that for the little LED on the side, which allows actually to measure all these nice things. Then there's another one, grain impact analyzer, which looks more for statistics, size distributions, and so on. I do not go into all the details, for otherwise we are just sitting tomorrow. And then there's a very special microscope which really goes down to below 100 nanosecond resolution, and actually can all the way down to 4 nanometers even in 3D images to look at certain dust particles. So to really for the first time see what all this stuff is really all about. And okay, then you have a spectrometer which looks more for neutral analysis with a rather high resolution. And I'll just go now a little bit faster through. Osiris, that's the camera I'd shown you the pictures from already earlier. And then you have an ultraviolet imaging spectrometer. What that's good for, you can analyze then the data by remote observations. So see what kind of material you have on the surface of the comet, and mainly interested in water, CO2, CO, and other parts, and how they changed when the comet approaches the sun. The next one is rather interesting also, and that is a microwave instrument which can be used, for instance, to measure the temperatures of the first few millimeters into the surface. And I'll come soon then to the first results of that, for we have done already the first measurements with this instrument and got some nice surprises out of it. And then we have a whole mapping system, so also more camera-based, together with high-resolution spectrometer in there, which is cooled down in order to be able to measure in the infrared. So what at this moment you can already see is there a large amount of cameras on board. And you all know what happens with cameras. Once they start taking pictures, you are flooded with data. And so the only limit is literally the sky, in this case a bandwidth of the high-gain antennas. And that improves, of course, when the whole thing approaches Earth a little bit. So, and this one is a very funny instrument which doesn't exist. It's what I talked about earlier, that they use these ultra-stable oscillators behind the radio link system on the orbiter end here on ground to look for phase deviations, and this figure there is just an example. What they're doing is they're calculating what it should be, verifying it with measurements while still far away from an object. And then, if the trajectory around that object or close to the object is favorable, then by deviations they can achieve a mass deduction even of these small objects of about 3%. It's rather unheard of. Normally, masses are calculated by looking at the orbits around the sun and using classic Kepler equations. That's how you get masses, but not to 3%. So that's real measurements, and there from also the mass of the comet was measured now. In order to do that, the trajectory initially, once it caught up in summer, became very funny. It passed the comet and then started to run a triangle in front of it. And tried to do that on, in front of a moving object here on Earth. It's rather difficult. You might imagine you have one plane and try to pilot another plane running in front of that one in a triangle. That's about the situation they had to fight with. And from the deviation of this triangle, they got then with this approach the mass of this. So as I said, there is a landing unit on there also. So what one wants to do is send it out. 11th of November is the scheduled date for that. And then send it all the way down from a distance of about 10 kilometers to a pre-selected landing site. I'll show you in a moment. And then come down there. And yeah, what happens? No one knows. Main problem is it certainly is not a granite rock. We hope it's not a piece of loose powder either, but something in between where you actually can land and not just fly through. It looks as if that will be the case. The earlier deep impact measurements from the Americans more indicated that there are comets which are so loose, dusty, that trying to land there would just mean you go through, come out of the other side, and probably crash into your orbiter which brought you there in the first place. So they were rather skeptic, but now when we are closer, we have a better figure about the density, so it's not that much of a difficulty. You'll see, for instance, this one arm coming out there, which is not quite correct, but anyhow. So what is the idea there is going away from this landed unit, hammering a rod into the surface, and then make differential heating to find out the thermal conductivity of the material as a function of depth. And for that, you have to go away from the lander, otherwise that influences the measurement. Rather complicated if you think about trying to hammer something into a surface without gravity assist. What normally happens is you lower your hammer, and actually you fly yourself backward. That's the only thing that happens. So it needs rather some ingenuity to do that. Okay. And then there are devices everywhere. This one used to be a film, which doesn't work here on the Mac. So that showed how this landing and initial operation worked. But I'll come to that here then in the detail later. But what you see here at least are quite some instruments on the top. These big cannons up there, there are actually thrusters, and smaller ones you can't really see in this resolution. Then they are the star cameras controlling the attitude and everything. And this blue thing in the middle, that's a lander covered by solar panels to power it up once the initial batteries are empty. So initially, it will just land and do everything with primary batteries, as they are called, for about 5 comet days. Run all the equipment, turn the thing around, and so on. So here we see a little bit better. So this is the schematics of that landing unit. You have this very funny landing gear, 3 legs, is only stable configuration, and each of them has a funny screw in there. Why? When it lands, we don't know what happened, but most likely the whole thing will just tumble over and fly away. So that should prevent it. So that by its own impact momentum drives these screws without any mechanics into the soil, and they seem to be extremely efficient. So they should keep it at least for a while. And then there underneath, there are 2 little red tips. They are harpoons, which are fired with explosives into the surface material. And then the harpoon wires are pulled back and should keep the whole thing then fixed. And in order to have all this process working initially, there's a thruster on top which pushes it down just in case there's already gas coming out, which it is already at the moment, and make sure that it really reaches the surface. And then you have this big tower there, that's the drill, in order to move down beyond the landing gear and then drill a hole and extract from down to 20, 25 centimeters below the surface and anywhere in between material which is moved up put into a gas chromatograph, mass spectrometer, you name it, infrared spectrometer, to find out what really the samples are, also what the isotope ratios, especially of water, is. For there's this big debate, can cometary water have contributed to the amount of water we have on Earth, which has a certain deuterium hydrogen ratio, or is it something completely different, which means do we find a completely different ratio? Initial measurements from the tails indicate that it is different. But on the other hand, what comes out is already mass selected due to relative speeds, so it might not necessarily tell anything about the composition of the actual material inside the comet. So that's why these instruments there are then tuned to find isotope ratios, also for light elements, which wasn't that easy. Then there's this APX instrument, which is lower down. It's actually running on all the Mars rovers also, and that's an X-ray spectrometer analyzing the material in detail. And then you have on this telescope this hammer I talked about. And up there you have some booms, a magnetometer in there, and then you have cameras all around with stereo view. And in these red circles I put around there, that are just the feet, which are very complex. They are my own, I have my own instrument on there. There are my own sensors in there with a multifunction. I'll come to that then later. And one of these is also in the lid of this APX instrument, and then around this Mupus pen. Mupus is the instrument name of this hammer. We have a network which does something. Here you have the actual flight model on the left-hand side, and such a foot opened. And you see there's actually a little preamplifier in there, which is rather a challenge for it has to work then also at minus 120 or at 0 and whatever. And additionally, there are piezo crystals in there which detect mechanical movements, and if there are none, there are actuators in there which can introduce mechanical waves into the surface structure and measure them with similar detectors in the navy feed, and thereby then getting a three-dimensional mechanical idea about the system. So my own instrument is looking for water ice content and its variation, so it's based on permittivity measurement principles, which were used this way also on Huygens, which was a lander on the Saturn moon Titan, a very similar instrument. So we are working with them together. They have a similar instrument on the orbiter. So basically what you do is you send some current into the system, and that introduces some potential or variations, and then you measure the amplitudes, phase shifts, and from that you get the idea about what kind of material there is. And if you use a proper frequency, in this case below 10 kilohertz, you concentrate only on water. For the rest, has much higher frequency responses in the megahertz range. So what we are seeing then, hopefully, is then how much water is there. We can use different combinations there for getting different layer information, and how that then changes when the comet becomes active. That is the whole idea of this instrument. So we get the electrical properties of the surface material down to about 2 meters depth, and the other instrument in the same feed is looking for the mechanical properties of this material. And both together define more or less how a comet is getting active. No one knows yet. There are lots of theories. There might even be different mechanisms for different comets. But at least for this comet, we hope with this combination, we should shed a light on that. So here is the actuator, once again in the black foot, which can actually use shear waves, introduce them into the material. So it's a rather flexible soul in order to translate these parts. On top of the whole lander, there is a little cube, which belongs also to our instrument group, which is covered, and this is white stuff around and at the top, by piezoelectrical plates, which are so sensitive that if you have a normal snowflake falling onto it, You register it, can find out what the impact velocity was and the mass. That was verified here on ground, and that's exactly what it's supposed to do. So what happens with dust floating around close to the surface before it can be detected further out at 10 kilometers, 20 kilometers, where Rosetta is flying? So putting both together, the idea is to figure out how this dust production mechanism really works. Okay. Now, MOPUS I mentioned already. There's this hammer in the laboratory, this whole Bronx system, and underneath you have our little mesh, which is measuring or actually used for putting currents then into the surface material. And that measures then, as I said, the thermal behavior of the upper 60 centimeters of the layer of the comet. And this is the APX instrument extracted, and the lid at the lower bottom, that's actually also one of my sensors. So when they are not measuring, then I can use this one here as an additional electrode to get different depth profiles. Okay, we have another instrument here, COSAC, which is this comet sampling composition experiment, which means it looks for complex organic material, which we know exists also on comets, but no one has ever really seen it in detail. For instance, the sample return missions, the main problem is that on the impact on the sampler, the dust grains get rather modified. So what we see here afterwards on Earth is no longer the original, but only a fraction of that. Okay, and then Triva, that's the camera, actually lots of them all around. And one is inside this little drill to make spectroscopic observations of the samples before they are put into the oven and destroyed and analyzed. And this one is the one with the high isotope resolution. Yes?
Just one short question. And all of this is powered with solar panels?
No. Okay, I can put, and I only mention it shortly. So what happens is that right now, the whole lander accumulator rechargeable battery is fully charged. And then the system is landing, needs a lot of power from the accu, and then eventually, once it's on the surface, the accu probably is empty, and then the primary batteries will be used for the first time to run the whole thing for about 5 commutator days. And 1 commutator day is 12.4 hours, and then after that, that's gone. And then the accumulators actually will be recharged from the solar panels and hopefully extend the mission for about 3 further months.
No OTGs?
No, it's not allowed, not in Europe. Okay, I go faster through here. And so some other, that's the down-looking camera, that's the magnetometer. This one is a very funny instrument. It's a tomographic instrument with one part sitting on the lander, one in the orbiter, and using radio waves sent all the way through the comet into the receiver on the lander, and from there transmitted the information then back. You get a 3D information like here in a normal clinic with X-rays. So after that, you see what the layering is, and so on and so on. So, and here you see what happened when the satellite approached the comet. And so that was from first 110 kilometers, and there it is coming slowly into your face. And the rest goes faster. So 12.4 hours is the rotation period, as one now knows, and it was discovered in '69. Okay. This one is rather closer. So it looks very funny, like a double comet with something keeping it together. And what you see on the right-hand side, these are brand new measurements. The mass was discovered by this, or measured with this radio instrument. So it's about 10 to the 10th tons. And the volume was was measured with the camera. and then modeled with a funny shape. And if you divide one to the other, then you come to a density of 430 kilogram per cubic meter. Just to remind you, 1,000 kilogram per cubic meter, that's solid ice, and about 240 that's loose snow, and that is somewhere in the middle. And the original estimates from NASA after deep impact was in the order of 100 or below that. So we are a bit more on the safe side. There is already water production registered, and at the moment it's about 300 grams per second. And this radio instrument Miro detected the surface temperature of minus 70 degrees, which is surprisingly high, which means it's rather black body. If it would be blank ice, it would be much, much colder, minus 120, something like that. So that's what we already know now, was published last week, basically. Okay, and then the big question, where to land. So these circles were actually pre-selected where it would be technically possible to land, and then last weekend actually there was a long discussion, well actually no, it's already 1.5 weeks ago, and the decision was made here. So we will try to land there on the head, the smaller part, and here you have it a little bit larger. So it still has quite some structure, but not too many boulders which could topple the whole thing. So far to the comet. And now a few minutes still to the data network part. So what do we do always with this huge amount of data? For once, of course, we get them down from different instruments. Each one has its own kind of format, and will store them in a way no one else can understand. And in order to understand what's really happening there, you have to monitor the comet from a distance. You have to monitor the sun to see all the driving effects. And this flotilla just on the ESA side, so European Space Agency assets, are doing that and providing data in lots of different formats and measuring them at different locations, different times, and so on. And on the left-hand side, you see the sun, partly looked at by SOHO. I have an instrument on that one also. But what does that mean? This is actually from the beginning of August, just a snapshot. You have the comet down there. You have Mars, Earth, Venus, you see it, Jupiter. And if you have some activity in the sun, an eruption, it normally goes into a certain direction. And in this insert up there, you see intensity distribution of these eruptions just normalized to the distance of the Earth, so just to give the direction. And there you see, depending on where you are, for instance, Mars, or then here our nice comet, there obviously nothing would have happened in this case very much. The main eruptions went into the other direction, so towards Mercury, Jupiter, and Venus, with some time shifts eventually. So what you need to do is taking those data, solar wind data, which driving the comet tail, combining them, taking into account this geometry, the time when they were recorded, the velocity in which the solar wind was moving, and the changes between 400 and 1,500 kilometers per second. And if it's charged, it follows the interplanetary magnetic field. If it's neutral, it goes straight, like the UV light which is recorded up there. And so it would be great to have a possibility to do all that without knowing all the details of all these different satellites I showed you just. And we have developed something like that in the EU FP7 program, or programs, actually several in a row, partly parallel. So this is now the idea of having data grabbed from, in this case, I think it's from Mars Express, yes, MEX, looking for plasma data around Mars, measured along this trajectory at a certain point in time, and we try to understand them. So we model everything, and then calculating the details what a satellite flying through this model would see. And this is a three-dimensional plot, or each axis is separate, and you see two parts are looking nearly identical, which is obvious for that's exactly one orbit period. So it comes back to the same location, which, if you look exactly, it has slightly changed, not very much, but it did a little bit. And then, of course, you would like to see how that was actually generated, how was that linked to a solar wind, and you have the same behavior also close to the comet. If you want to know what happens there, you need this kind of superposition possibilities. Grabbing the data, these data are actually in Madrid, or close to Madrid in the ESA Science Archive, ESAC. And these models were taken actually from our data server in Helsinki, for the output of one of our models, and selected half automatically according to boundary conditions the scientists who made that selected in order to figure out, does that match the observations? If not, you go back to look for something slightly different. And here you have the same thing with Scala. And now the last 3 slides are for the implementation. It's actually here a virtual observatory for these purposes, just concentrating now mainly on the plasma aspects. So what you have is the normal interactive web interface on the left-hand side. The user specifies, and might even have its own workspace where you can come back the next day, and specify what kind of data he wants. And then the system is looking for something and makes some priority ranking, and fetches data from the huge amount of stored data. Each measurement cube of a model takes about 200 to 400 megabyte. So it has to go through there, and then the best match is sent back and can be visualized. But that's not why I'm showing that here. For the other part, it's much more interesting. You have this data access system, which fetches data from Mars Express, from the different archives, and possibly from solar observatories to find out the source of solar wind, matches the speed, times, and so on top of one another. And then, looking at that, you say, now I want to have a model for that. So it goes the other way, sends directly from the server there, via a special planetary data access protocol, a request, which goes in here, and if necessary, it even interpolates along the theoretical trajectory of the satellite, if the interval was given in time, and then returns those data, or actually stores the data in a temporary file, and returns a direct URL to that file, so that the server can grab it and overlay it over the measurement data. And that part all works now for many different aspects, planetary data, atmospheric data. And behind that is a very complex protocol with registries at different places, but distributed registries. So top-level registries in the central part, but detailed ones then at service. And by doing that, we don't have to transfer 500 megabyte of data, but perhaps if it's just a vector plot you want, might be 20 kilobytes. That's the only thing you need, which is a nice thing thinking about network bandwidth. So that's the basic idea of this planetary data access part, to do the filtering on the archive side and provide only those data the user really needs, and what the user needs is more or less interpreted already at the workstation level to find out in proper coordinates or parameters accessible or understandable by the system. And this is how it's actually implemented. And so everything the user sees is outside our firewall, and then the information you request is put somewhere in the file, and from the other side of the firewall, routinely, inside a second or faster, these are grabbed just to make sure that no hacker can go in there. The data are interpreted. If they are wrongly formatted, forget it. They might even run on request a fast model update and return the data onto a big data storage, which is visible and if it's read-only mounted through the firewall to the other side and then returned there. And what I just said, that might take everything between a fraction of a second and a day if you run really a complex model through our supercomputer part.
radio downlink from the spacecraft, do you use a deep space network or do you have a...
Yes, I will. Thank you.
Yep.
What about the radio downlink from the spacecraft? Do you use the deep space network for that, or?
No, it's actually for that. It's initially a deep space network, but after that there is our own antennas, which reduce the bandwidth a little bit, but it's cheaper for the Europeans.
I see. Okay.
That's right. And this one is a final picture, actually, and that's what this whole business amounts to. So this was a publication, Science Direct, and down there on the right, you have from the spacecraft different plasma parameters, these red ones, overlaid with the vectors grabbed from the model along the same theoretical trajectory. And if you want to know how the model itself looked like, this three-dimensional cube with lots of parameters, you see this yellow part up there telling the, in this case, Mars environment, how the plasma really looked there. And now you have to imagine through this complex color 3D plot, the simulated spacecraft trajectory was cut through, and along this line, the data were grabbed and put down there into this overlay. And the whole thing, you have 4 websites there. This overlay is done in AMDA. The modeling access is done in IMPEX. The Rosetta part you can look, for instance, at through our website, also with links to ESA and so on. And the whole networking business I had been managing in the FP7 program called Europlanet in order to get hold of all this stuff. Thank you. Right. Yeah.
What sort of bandwidth do you get from the satellite up there?
Pardon me?
What type of bandwidth are we dealing with, download-wise?
Yes, the download from. Let's start with a simple one from the lander up to the orbiter. That's 16 kilobit per second, and then from the orbiter down to ground, that depends very much on the distance. And it's in order of a couple of megabit per second, even up to a gigabit per second, when we're getting closer. Let's change mics. Yep, thank you again.
Test. Yep. So following probes and spacecraft, that's what I consider a tough act to follow. So I'll give a presentation on something a bit more down to earth and mundane. My name is Anders Rode Gregersen, and I come from a Danish wind turbine manufacturer called Vestas. And I'll talk a bit about how we are using data to drive our business. It's not obvious why the world's leading wind turbine manufacturer is investing heavily in supercomputers and big data systems. So that's what I'll be talking about today. And I encourage you to ask questions along the way. I much prefer the dialogue over the monologue, so don't hesitate to ask questions. So I'll start with a brief introduction to the main characters of this talk, then followed by a brief introduction to why it is that we got started with high-performance computing in the first place, then talk a bit about our big data system, and then talk a little bit about how we actually do this, considerations on usability and capability, and then show a little bit about data-driven decisions, exemplified with useful example. Okay. My name is Anders Rode Gregersen. I'm Chief Specialist at Vestas I'm responsible for our HPC and our big data installations. Before Vestas, I was doing sensor data at in the scientific arena. Yeah, I guess that's about it. Next up is Vestas as a company. Just a brief introduction for those of you who are unfamiliar with it. We are the largest wind turbine manufacturer in the world, with a total installed capacity of some 60 gigawatts. To put that in perspective, that's approximately 12 times the energy usage in Denmark. So that's considerable. So typically one fifth of the wind turbines out there is a Vestas turbine. And what's interesting to this presentation is that 47 of those gigawatts are being monitored by Vestas. So that's some 26,000 plus wind turbines that constantly sends us signals. I should also mention that we are a company that works with a vision of a planet where we have wind on par with oil and gas. That way, making it so much easier to make the right choice of choosing energy that is based on that are carbon neutral. Well, I will also give a brief introduction to the final character, and that would be the wind turbine generator, because when I talk about sensors, it's not scientific sensors as in Walter's presentation. It's just measurements. But what kind of measurements? Well, we have all sorts. A modern wind turbine has some 500 signals. But there is a huge difference in the sampling rates of these sensors. So, I mean, take something like wind speed and wind direction. It doesn't make sense to have this at a kilohertz level. Whereas when you're looking at accelerometers, it does, and especially when you're looking at converter subsystems, it definitely makes sense to have a very high sampling rate. So just to give you an idea of what it is, I mean when I'm talking about sensors. Okay, so let's start out with talking a bit about why does it make sense for a wind turbine manufacturer to focus on high performance computing and data intensive computing. Well, it boils down to the vision that I mentioned before about a planet where we have wind on par with oil and gas, and then down to what is it that matters for our customers. Because why is it our customers are buying our wind turbines? Is it because they produce green carbon neutral energy, or is it because they have a beautiful shape? None of the above. It's all about return on investment. So it's investment objects for them. And as such, we are to provide them with a reliable return on investment. Otherwise, they'll just invest in other investment objects. All right? So nothing new there. It's always been like that in this business. So normally what you do is when you have to estimate the return of investment on a wind turbine, well, there are a number of things you need to know. I mean, first of all, how much energy is there out there to be harvested? That will give you an estimate of the sort of revenue that you can generate from a wind turbine generator. But also, that sort of energy that you can harvest, is it a good one? Is it a good form, or is it a turbulent form that will wreck the turbines and thus decrease the expected lifetime of the wind turbines? The normal way that is done in the wind business is that when you ask such a question, whether it would be a good idea to put up a wind turbine at a particular location, you set up a MET-mast, a meteorological mast, where you have some measurement equipment in, and that will have first of all, there's a direct cost there of 200,000 euros on just erecting it. But even worse, there is an opportunity cost in you waiting 18 months to get the data home from the MetMast, because you need to get the seasonal variations of the weather patterns and stuff like that. So there are a number of challenges to using that approach. And to make matters worse, it's only a point measurement. You can only reliably say anything about the measurement point that you got right there. All right. So what we do instead is we are part of the meteorological community in the world at Vestas, and as such we have access to meteorological data. So we have some 35,000 measurement points around the globe dealing with weather. I'm afraid that the Finnish meteorological industry, I don't know if we are working together with you guys, but we may. Anyway, we have access to the to these 35,000 measurement points, and then we have a powerful computer where, just as your local weather service can do forecasting ahead of time, you can also solve the same differential equation back in time and then couple it with the actual measurements. So instead of doing a forecasting, you are doing a so-called hindcasting or reanalysis, where you are solving the same equation systems, but you are making sure that they satisfy the 35,000 measurement points you got out there. And thus, unlike the forecast, where the forecast gets more and more uncertain, you can stabilize your uncertainty. Okay, so we have a mathematical model of how the weather systems have been on this planet, and we have done that all the way back to turn of the millennium. So from this mathematical model, we have then measured performed virtual measurements on the planet down to a square kilometer level for approximately 200 parameters at an hourly basis. As you can imagine, that accumulates to a lot of data. So that we have on a global scale. Here I'm giving you an illustration of this for one parameter over the Nordics. So we do that for a global scale. So if Walter was to give me the coordinates set to his backyard, I could tell him all about weather conditions, how they have been in his backyard, despite the fact that there's never been any measurement equipment there. Next thing we do is on a side-to-side basis, we do normal CFD. Let's see if this will work. It won't. Doesn't matter. We do fluid flow simulations in order to find out how turbulence is at the sites. So the former thing I just spoke about was about finding out how much energy resources out there to be harvested. This is more about how to position the wind turbines in relation to each other. And in particular, how not to put your wind turbines in a location where you have turbulence. Okay, so the Vestas approach is different from the MetMast approach in such that we have this gigantic database with atmospheric data for the entire planet, where we down to a square kilometer scale have hourly measurements since the turn of the millennium of approximately 200 parameters. And on a side-by-side basis, we have a thorough understanding of exactly what happens down to the meter cube scale. All right. So that's and what this data does is that it supports us throughout the entire value chain of the company, meaning it supports us from the project phase, where we are helping the customers setting up, finding the proper locations of the wind turbines, to the operational base. Yeah, there's a question.
So, what's the accuracy of your predictions backwards compared to a MetMast?
So they're actually quite good. But they become even better because what actually happens is that we are a bit ahead of the business, to be understood in this way that typically when people want to invest in a wind power plant, based on some 100 wind turbines, the investor only has like 10% of the down payment. So what he does is he goes out on the fiscal markets and then lends the money. But in order for him to lend the money, the financial services, they demand that he gets an insurance for his investment. And the insurance companies are very conservative by nature, which makes sense. So the only thing they believe in are metmasts. So eventually a metmast will be erected, most likely, at the site. But by that time it is being erected, we know all about what to expect from the measurements. However, what it gives us is, it gives us the direct measurements from on-site, and then we can long-term correct our virtual measurements with the actual measurements. So that's how it typically goes. But it has all to do about us being a bit ahead of the business, and it just takes time to settle. Okay, so I was talking about the business cases for this because, I mean, as I mentioned, this started in the project arena where we are looking into enabling more cells of our wind turbines. But it has actually, today it is supporting us in all kinds of ways throughout the value chain, because we are not only using this, I mean, in the project phase, we're also using this for operations, because as we are doing these hindcasts, we're also doing forecasts. And with forecasts, we can do super accurate estimates of the power that is being produced the coming week from a wind turbine park. And that helps us make the power that comes out of the wind turbine so much more valuable to our customers, because then they can actually sell the power before it is being generated. So a bit about how that fits into the business. Okay, now talk a bit about the big data analytics that we are doing on our data here. And just to draw up the data landscape at Vestas, I mean, we have all sorts of data, as most companies. And as you can imagine, this amount of data that we got generated from the mathematical model of the atmosphere on the planet, I mean, it's enormous. It's 200 million gigabytes. So it's, I mean, you cannot just have a regular relational database crunch those numbers. So we needed something special for this, and this was back in 2010. So this was before big data was completely overhyped and misused as a term. But we needed a big data system to handle this, and that's what I will present to you right now. What we did then. And it has to do with the simulation and prediction data that we have in the bottom part here. But there's much more data at Vestas. We also have the measurement data from our wind turbines, and I'll talk a bit about those later. Just to draw out the landscape. Okay, so building this database that could scale beyond petabytes, we had a number of use cases for it. So first of all, one of the driving use cases was these point queries. We wanted to be able to sit down with the customers at our sales offices in different countries, and then have our salespeople sit down with our customers, and then they could click on a potential position, Walter's backyard, and then put up some virtual wind turbine generators, and then find out exactly what the business case would have been had they erected these wind turbines in the year 2000. So point queries needed to be ultra fast. Then we also needed a system that could actually that could embrace the entire corpus data. That if we needed a query that touched every single measurement point on the planet, we needed a system that could handle that as well. And then we also needed it for high frequency data on forensics if you are doing a post-mortem on a wind turbine that broke. Okay, so regular databases and regular data warehouses are just not, they're not built for this sort of this sort of problem. They don't scale neither conceptually nor economically. So and actually we had a big vendor try to work out what it would cost us to build this on normal database technology, and by the time that it ended in numbers the size of a GDP of an African country, they stopped. So I mean, it just doesn't scale. Okay, so the business challenge is that we have some 200 parameters, these hourly measurements, lots of data basically, and what we need is relational database-like functionality, fast point queries and scalable queries. So at the time we were in negotiations with IBM on buying the simulation hardware for the simulation problems I talked about earlier, and through those discussions I came into contact with people at their research facility in Almaden, the location where the relational database was invented back in the 70s. And they were actually looking into some of the same problems that we were having. They were just looking at it because it was interesting. We were looking at it because it was our headache. So there was opportunities here for a win-win situation. So we developed a partnership where we moved people over to Almaden, and together with IBM worked out a system. And mind you, this was back in 2010. So it was before the open source versions, the open source Hadoop solutions were at the state where they are today. So it was a correct time for such a partnership. And the reason for the partnership was that we got software developed that matched our needs, and software that was carried by multiple customers instead of just us actually dealing with the entire lifting the burden of developing all of this. So how do you work with a system like that? Well, at that time, it wasn't. You didn't use SQL to ask questions, and that's a bit of a problem when your workforce is used to working in SQL to formulate their queries in SQL. So we got something instead that was called Jackal, which is actually a superset of SQL. You can express the exact same things as you can in SQL, and as those of you who are familiar with SQL, it's potato. It looks same but different. Okay. So what does it give you when you all of a sudden have access to this sort of data? When you have when you know all about weather system historically on the planet? Well, let me illustrate you what this gives to the business. I mean, besides what I've mentioned. So here, what we got here is a heat map for a location in the middle of the mountains in central China, where we're looking at a heat map going from blue, unlikely event, to red, very likely event, and where we have mapped at the first axis time of day, going from midnight to midnight, and on the secondary axis we have the time of year, so going from January 1st to December 31st. And what we're looking at is a particular phenomenon called hydraulic jumping, which is harmful to our wind turbines. And normally we would just put up our wind turbines, and we will find out we'll find out once wind turbines entered production, and we would have extremely high service costs on the wind turbines. Now, even before a truck has been in the mountains of China, we can engage with the customer and then say, okay, so something is happening in the noon hours in January. We have very much hydraulic jumping occurring here. What do you want to do about that? Should we curtail production? Then you will lose this and that much income. However, it will give you this and that much more lifetime to the wind turbines, or what should we do? The whole idea here is we can quantify this. We've taken out the guesswork and made this tangible. Yeah. Okay. So what sort of architecture do you need to drive a wind business on data and simulation? Well, here we're looking into one of the cold dials of Firestorm, the computer that we're using for this. At the time of the installation, it was, well, actually still, it's still the biggest computer in Denmark, and at the time of the installation, it was the third largest commercially used computer in the world. Install time, that was the summer of 2011. So I guess with this sort of audience, you are fully aware of how you build a supercomputer capable of running memory-bound problems. So I'll not talk too much about this, but these are the factoids about our machine. The usability challenge. So as I mentioned, this is a tool that is not only being used by PhDs, but actually it's being used by common salespeople as well. So what do you do when you have something that is complex, but you want to have regular people use it? Well, well, the normal way of fixing this is wrapping it into a GUI, and actually we have succeeded with this, so that we can approach both kinds of people, both the PhDs who want the devil in the details, so the terminal way, the terminal-based way, and the graphical user interface. So actually, most of our users, they are unaware that they are running on a supercomputer with a gigantic data backend. So and building up this capability, we started back in 2003 with first looking into computational fluid dynamics. But it took all the way till 2007 before there was any any correspondence between what was simulated and what actually happened out in Mother Nature. And first then, it made sense to actually truly build up this capability. So in 2008, the proof of concept machine was built, which at the time was a sizable machine, but it was mostly for proving the concept in this. And after running that for a couple of years, management investors decided to go full steam ahead on building up this high performance computing capability in the company. So yeah, so it's nice with all this data, and to make sure that you got something out of my presentation, I wanted to make sure that I could at least present some data that would that you could make some use of. So what we got here is again a heat map over. This is over Europe. You got I don't know if you can tell the lines, but you have Northern Africa at the bottom part, and then you have the Italian boot in the middle, and then you have the Nordics in the top up there. And again, what we got here is a heat map of where I've taken the July month, every day in July for the past 14 years, and then I've looked at the probability that the conditions that we wanted satisfied, put on the left-hand side of the slide, is satisfied. And what I'm trying to help you guys with is to decide on where in Europe to have your next vacation. And I mean, a sensible thing to have in your vacation is sun. I mean, of course you want sun. So the first condition that I put in was we want at least 10 hours of sun a day. And mind you, what I've done here is for each square kilometer, I have taken every single measurement in July. Then I've looked at, okay, so that's some 300 days a point. And then I've looked at each day, have there or have there not been 10 hours of sunlight? and then made it as a probability over the past 14 years. Okay, so as you can see, it looks actually pretty nice in the Nordics. Okay, maybe not in Norway, but at least in Denmark, it looks as if Denmark is just the greatest place to have vacation. We have plenty of sun. But I guess there's a reason why Danes, they move away from Denmark in the month of July. It probably has to do with this, because if the next condition that we put on is then, well, we also want it to be sort of warm. So somewhere between 25 or 30 degrees. And then all of a sudden you can see a different picture, right? Low probability of that ever going to happen in the Nordics. So perhaps there's a good reason for going southwards. Well, let's put on one more condition. We also want it to be calm, so we don't want it to be too windy. And all of a sudden we see a picture of the places where we normally go on vacation, I guess. So we have the Iberian Peninsula, we have Italy, we have Adriatics. But what we can do is we can just continue to zoom in, because I mean we have this down to a square kilometer scale. So now we can look at Italy, for example, and the Adriatic coast, on where we want to go there, and we can just zoom in. I mean, just continue to zoom in. So, but I wanted to end off with a heat map that showed that it can also make sense to have your summer vacation in Denmark. And if you like windsurfing, which means lots of sun and lots of wind, well, Denmark is the place to be. So so that concludes my presentation. Hopefully you'll have some questions. Thank you.
Thank you for a great presentation, and also very impressive that Vestas is able to crunch all these numbers, and as I understand it also from other presentations, actually sit down with the customers and in 5 minutes pinpoint a location where you can set up a wind turbine. On the other side, I'm a bit disappointed, because when you take this on where should I go to vacation, where should I take my family to, and you pinpoint, well, Italy could be a good place. The big data challenge will then be, oh, should I drive to Italy or should by plane, and which kind of hotel, and use the social media to interact with the big data to give me this opportunity to say, well, I would like to go with my family to Italy, to Rome on this week. That will be a great challenge if you can give me this.
Certainly, certainly. I've only mentioned the technical problems in this, on how we sort of solve this problem of having a large data volume, and all of a sudden enabling that data volume to be curable, so that you can actually gain insights from that volume. But that's only, I mean, that's only the tip of the iceberg, because the next thing that we're working on right now is bringing not only this virtual measurement data, not only having this capability on the synthetic data, but actually bringing in all of the other data. So the sensor data from the wind turbines, and coupling that with these virtual measurements, so that you can make queries that span silos. Right, so you have the measurement silo, the Venn diagram that I showed you earlier. Yeah, so you can begin to ask questions that spans different data silos, and that is where true insights and true value for many businesses lie hidden. But it's also extremely hard, because all of a sudden you are looking into, I mean, lots and lots of problems. First of all, I mean, the technical one of bringing these sorts of data sets together is, I mean, this is the easy one. I mean, think of the political issues of data used to belong to one department. Now all of a sudden you want to bring data together. Think about data veracity. I mean, If it's crap in, then it's crap out, stuff like that. And so, I mean, there are plenty of issues in big data, and that is also why, I mean, it's good we are where we are with regard to big data. I don't know if you're familiar with the Gartner hype curve. Yeah, okay. So big data used to be on the totally inflated point where, I mean, you can use big data for anything. I mean, it can brew coffee underwater, and it can do everything for your business, and it can't. And now you are moving into the valley of disappointment, where, I mean, so you invested in big data, and now it can't solve all the problems for you. Well. And then after a while, I mean, you sort of begin to find out, okay, where does this have true value? I believe that where it has value for us, is it solves problems with regard to volume. The next problem that I'm trying to crack now is I wanted to solve the problems that we have with data variety. Because many of the problems that you see with bringing data together is that we've been used to working in a very rigid world where it's schema based, right? So if you need to set up a database quick, that's not going to happen because you have a strict enforcing DBA with schemas in mind. And what you can all of a sudden do with this new data model is that you can have this data reservoir where you're just putting up data, and all of a sudden you are enabling enabling yourself to gain insights from the data, simply because instead of the relational database method where you are thinking really hard because you want to optimize your resource usage as much as possible. I mean, mind you that the relational database was invented in the 70s where CPU resources was really expensive. So you would do anything to avoid a full table scan, whereas the modus operandi here is the complete opposite. No matter how simple a query, I mean, you're going to scan anyway. You have a big computer now to scan it, so it won't take long, but you're scanning anyway. So once you turn that around, then all of a sudden it becomes so much easier to bring varied data sources together. So that's actually what I'm working on right now.
If I can allow a small question as well. I think the presentation from Torben Andersen and your presentation today bind things together, because if I understand it correctly, this is, if you put it Vestas in a smart grid, the challenge for Denmark is the fluctuation in power supply and in demand, and well, you have to reckon, and you have to have models to forecast the demand and the supply. And you're also working in forecasting and modeling this. And in your last slide, I think it was 2006, you started off with a model, and 2011, the model was so mature that you actually can use it for production and sale. So it takes very long time and develop. So what can we start off, maybe you know it, in Denmark we start off with this new national supercomputer, and we'll really like to develop supercomputer into new fields like humanities and social science. Should we expect a 4 to 6 year approach until we have a model that is reasonable and is consistent and mature enough that they can actually work on? Or what should we expect for time scheduling here?
So first of all, the models that we're talking about relate to the simulation part. So I don't know if you were talking more about the data. So more in general. Well, it always takes time. It always takes more time than you anticipate. I would say. So I think what we did was that we had a very targeted approach. So the proof of concept machine, it was very narrow what we wanted to use this for. In order for us to prove the benefit of this, once you get that, So instead, so it's a bottom-up approach. You take the you take the low-hanging fruit, gain your insights from that, and from that you make it much more. You make it so much more easy for yourself to argue a top-down approach on why you should invest in this, because I mean many companies with big data becoming hype has done the exact opposite approach, right? So they look at what's the most fashionable buzzwords out there at the moment. Big data. Okay, so we need big data. I mean, with no clue as to what value it's going to bring. So my suggestion is go the other way around. Find out where that low-hanging fruit is. Deliver that value, and then from that you can build it grander and grander, and so. Yeah. But it is interesting. So I take it that you are involved in data at a national level. Yeah. So I mean, and that is truly interesting, because I mean, someone who should be truly looking for insights in data should be our scientists, right? I mean, that's practically what we are. That's at least some of the things you're trying to achieve as a scientist. So one thing is, I mean, well, Walter is out there getting new data to us so we can become more enlightened. But what about bringing down the silos so that we can get all of the insights that lie between the silos? I mean, on the already present data. I think there's much to be gained from that. The problem is that that's not a technical issue. That's one of those hard problems that are talked about. So.
Just have one question. I come from Norway, and of course we're a very carbon-driven economy. Mm-hmm. So I would recommend you buy some shares in Statoil, for instance, so we can make sure you get more wind. Joke aside, this looks to me very much like the seismic data that oil companies need to mm-hmm. try to find where to drill. But what I'm wondering is more from a business perspective. Will you be buying, or will you be buying CPU time or cloud services for your next supercomputer? Do you make that kind of decision? Because lots of time and energy must be going just to operate these huge machines.
No. So actually, this machine has an incredible utilization. I used to work in academia, and this machine, despite us trying really hard to have high utilization, and the utilization was high on the academic machines, this is by far, it's even higher. So this is in the 99%. The reason for this has to do with the reanalysis jobs that I mentioned before. So the reanalysis jobs are tiny jobs. They only span 48 cores, and there are a gazillion of these small tiny jobs. So what they do is that once you have scheduled the big jobs, then you can just fill the rest of the machine with these tiny reanalysis jobs. So I mean, it's because of the workload. It's fairly easy for us just to top up the machine, and we still have a lot of those we have a lot of that workload still to be calculated, and that's why it makes sense for us still to have a capability machine that we can then top up with these smaller jobs. But we are looking into whether we can cloudify some of our calculations, because what we see is that the cloudable instances are now becoming so fairly big that you can take one machine, and if you are willing to wait 3 to 4 times as long as you are now on solutions. Let's take, for example, the computational fluid dynamic rendering that I talked about. What we do there is we have some 36 wind directions where we are simulating what happens at laminar flow into a park at a kilometer scale level. And each of these directions today is being run simultaneously on our supercomputer. But what you could imagine in the future was that each of these directions were just put on one gigantic or one cloud instance, and then running within the limits of that cloud instance, taking longer time. But if you're willing to wait a bit longer, then you can do it that way. Yeah. So yeah.
Yep, one comment. But we run into setting similar things up meteorologically, but also especially with our space data, is this huge amount of data. In order to combine them, would basically, for instance, make grid computing useless. For the computational part will be only a small part of the data transfer. Mm-hmm. So what we did in the planetary community and astronomy community is going the other way around, doing pre-filtering completely at the archive levels, and then doing all the combination on the pre-filtered data in order to reduce the amount of data to be transferred. We're doing that now also. Actually, the EU decided on that in meteorological data, which means making all the data archives intercomparable so that you can query them selectively and concentrate then the model runs on only a subset of the data you need at that moment, which shifts the processing environment rather into a different direction.
Oh, it does, because I mean, essentially what you're doing with a Hadoop system like this is that you are having the processing goes to the data, right? Yeah. Because essentially the problem today is that we have a hard disk interface that just hasn't changed much. I mean, the first hard disk I got was 42 megs, and you could race from one end of the disk to the other end in minutes, right? Today, if you go out and buy a 6 terabyte disk and racing it from one end to the other, then because that interface hasn't changed radically, I mean, that will take hours. It will take most of a day to race that disk through. And so you begin to circumvent that by building up systems where you are having data being raced through on hundreds or thousands of disks simultaneously in order for you to gain that bandwidth to trawl through all of that data. But if you embrace the way of working by working harder instead of working smarter, the problem is the working smarter. We tried that since the 70s, and right now we are at a level where the amount of data, I mean, if the amount of data is so huge that you can, I mean, you try to work smarter, but you can just not retain all of that in your head any longer, then at some point then you just work harder. That's essentially what happens with the shift between relational databases and Hadoop. And that's also, and let me finish off by saying, it's not one or the other. I mean, if I could solve my problem on a relational database, I would do that, because, I mean, there are so many nice features you can get out of that. But once your problem exceeds a certain limit, yeah.
I really hate to say this, but we have to end this session pretty soon, so let's thank Anders for this. I hope we would have sessions like this every day, but unfortunately we only have them every second year. But there's something we can still do today, so there's the conference gala dinner. So please remember that. That will start 7:30 at the Uppsala Castle, and I hope to see you all there. As a small practical thing, there's a bus transportation to the dinner venue, and that leaves the hotels at 7:10. And there's another bus which leaves from this place at 7:20. And as you might remember, you should have registered to these buses already by yesterday. But it's a short distance from here, so I think it's not that a bad idea to walk there. So thank you very much. Let's continue the conference tomorrow at 9 o'clock. Have a nice evening.
It's really difficult. I don't understand anything, but none of the staff do. We've been joking about like trying to redo the lecture to each other every time, and whoever like can get the most of the lecture wins. Och?